some problems in the book. If you have your book, you will need to open up to, we're on chapter 9. And we're on this kind of weird word. You guys know, anybody know how to pronounce that?
Stoichiometry.
Stoichiometry. Yep. Page 299. This is the plans for this week. We'll do some problem solving today. We'll do some extended problem solving tomorrow to kind of finish up this idea of what we're doing now. What we're going to start doing today and expand upon it tomorrow. On Wednesday, we'll give you an introduction to the lab you're going to do. And then kind of introduce you into what's called limiting reagents. Start doing some of those. Then the quiz will cover what we covered today and tomorrow. So the quiz on Thursday, I won't be here on Thursday, but the quiz on Thursday will cover what we're talking about today and tomorrow. Okay? On stoichiometry. And problems that you'll be able to have done enough of those that you should be ready to be able to do one of those. Okay? Then Friday we'll do a lab. Okay? Friday will be a lab based upon concepts that we'll go through today and tomorrow. Okay? And you'll just go through and you're going to do a reaction. You're going to weigh out your reactants or reactant. And you're going to weigh out your product to see, and then see how close that your weight is compared to theoretically on paper what it should come up to be. Okay? And we'll do that on Friday. There's only 2.5 weeks left before the end of the 9 weeks. Seriously. Okay? Yep, 2.5 weeks. We get, I think it's, there's a couple days you guys have off after that point in time, and then we come back and we start the last quarter at that time. Okay? There are 2 words at the top that represents stoichiometry. And all stoichiometry is a relationship between the mass of the mass relationship between the elements. Now, we're going to look at mole relationships today, but they will correlate into mass relationships. All right? And if you remember, we did some composition stoichiometry already. Okay, reaction or composition stoichiometry it involves just the individual formulas and how the weights all relate. Like if I had H2SO4, then I could look at their percentages by weight, which I can find what's called the percent composition. And that's kind of like composition stoichiometry, right? I can add everything up. You don't have to do this, but this is an example. I could add up to 2 hydrogens. I can add up the 1 sulfur. That wouldn't be sulfur's weight, though. I'm thinking oxygen there. So, sulfur I could do 32.07. Then I can do 4 oxygens. And then I get an answer would be 98.09 grams. And these would be the weights of each one. And then I can find the percentage if I wanted to. And so all of that has to do with composition stoichiometry. We've already done that. We're not going to do it. But just for your reference, that's what we look at with composition stoichiometry. Okay? The reaction stoichiometry is a little different. it's using a balanced equation. Okay? So it's looking at relationships between weights of a balanced equation. If you would turn over to the problem that you were asked to look at and to do, you can turn over to page 306. So go ahead and turn over to page 306 if you would. Okay, so at the top, you've got a reaction you were supposed to write out. Okay? The reaction would be taking nitrogen gas plus hydrogen gas gives you ammonia. Ammonia is a prime part of what's called fertilizer, and of course in the state of Nebraska and in the Midwest in general, probably a lot of different places in the world, to get the crops to be better, more yield, to produce more of it, which means more money. They have to put fertilizer into the ground, and for it to be there for when the crops would need to be access to it. Okay? And so ammonia is part of that. So if we would go ahead and balance this equation, we just put a 2 in front of NH3 and a 3 in front of H2, and it's balanced. Okay? So we can relate all the weights if we wanted to. Right? So I'm going to do this. You don't have to write it down. But we could relate all the weights, which is called reaction stoichiometry. If we had 1 mole of N2, that's 28.02 grams total for just the N2. If we have 3 hydrogens, and we would weigh all that out, that would be 6.06 grams for just the hydrogen. Okay? Which on this side is going to be 34.08 grams total. So the other side is going to have to equal what? 34.08, right? So ammonia, when you add it all up, it's 17.04. So when we do that, we had 2 moles of it, that would be 34.08. They equal. And so we know that when we do a balanced equation, we know that we're proving the law of conservation of mass every time. The weight on the reactant side will equal the weight on the product side every single time when we do that. Okay? So we're going to simplify it a little bit, where we're going to deal with mole relationships to begin with. Okay? So I'm going to go ahead and rewrite this, and just we'll look at one problem you were supposed to do, or 2 problems you were supposed to do, and then see if they make sense now that I'm going to go ahead and show you what you were supposed to set up and what it was supposed to look like. Okay? So again, we have N2 plus H2 gives you NH3. You already have that written down in your notes. And these become numbers out in front are moles. So they asked you to do a problem earlier where you had to look at a mole ratio. So here's 1 mole ratio. Okay? I'm going to compare nitrogen and hydrogen. So I can either write that ratio as this, or I can write it like this. Those are mole ratios. Okay? Kind of like a fraction, but you're going to use it in which to do some problem sets where you have to maybe find out how many moles of a certain reactant or product that's made, like in this first problem. Okay? We can also look at the ratio between hydrogen and ammonia. So we can also look, let's go ahead and do one like, we can say for every 3 hydrogens, you get 2 ammonias out. Or you could write it for every 2 ammonias, you have 3 hydrogens. So you could write it that way too. And that would be the mole relationship between just 2 different reactants and products. So this is going to be, these ratios are you're going to use in solving a problem here in a second. Maybe you've already done it. You can check the answer to see if you did it right. Okay. So again, we're looking at the problem at the top of page 306. And we've got the equation written out. We got it balanced. That's the first thing you need to do. Okay? Have it written out and balanced. And then what you need to do is when you set the problem up, you're going to use this ratio, bottom ratio, to determine the answer. Right? So it says that you have 6 moles of H2, right? So it says in the problem. Right? And it says how many moles of ammonia is going to be produced. So, when we take a look at our equation, we're going to put our mole ratio in this fraction, and then we got to be descriptive of what we need to cancel out and what we need to find. So, moles of H2 need to go down below because they have to cancel out. And then up above, we need moles of NH3 because those are the units and that's the product we need to find an answer for. So what numbers go in for, what number goes in for moles of H2? 3. You look at your balanced equation. It says it's 3 to 2 ratio. So this is the one we use here. 3 to 2. That's the ratio we use because we need to find ammonia. So this is the ratio we're going to have to use. So we've got our 3 there. And up above we'll put 2. And then our units are moles of NH3. And so the moles of NH3 would be how much? So 6 times 2 is 12, divided by 3 is what? 4. That's our answer. Okay, questions? So that's the answer. Now we don't have gram relationship. We're not doing weight, but could we find the weight of 4 moles of ammonia? Yes. And you're going to have to do some problems where you're going to have to take this one step further, and we'll do that today before you go. All right, any questions on that one? The next one you had to do involved the decomposition of KClO3. That's problem number 2 at the top. It says it decomposes into oxygen gas plus, it doesn't say the other product. The other product's KCl. So when we balance our equation, it goes 2, 3, 2, balancing. You guys know how to do that? In good shape with that? And so it says that it wants to know how much potassium chlorate is required to make what? Go ahead and read it.
15 moles of oxygen.
15 moles of oxygen. So we need to find the ratio between KClO3 and oxygen. What is it going to be? A 3 to 2 ratio, or in this case probably a 2 to 3 ratio because depending upon how we want to set it up. So out in front of it, but 15 moles of O2 is produced. And it wants to know how many moles of KClO3 it's going to take to make 15 moles of O2. So we're going to set up our conversion, and we're going to put our mole ratio in that next slot. You guys go ahead and do that. So again, I have moles of O2 and moles of KCl3. So this should be a number what? 3 to 2. So I'm going to divide by 3, which is 5 times 2 is 10. Answer's 10 moles that are produced. And that's all you're doing on most of the assignment today. You're just doing one step. You're canceling out the moles that you start with so you can find the moles of another reactant or product.
So how do you get the 2 to 3?
3 and 2 comes from my balanced equation.
Okay.
That is my ratio.
Alright.
It's saying for every 2, this one's saying for every 3 O2s you produced, you need 2 potassium chlorates to produce each 3.
Okay.
And so that gives you a ratio so you can do the calculation. Alright? Now, we could take this a step further and figure grams. So let's state the question is not how many moles of KCl3, but how many grams. We would go ahead and continue on with this step, but finding grams instead. So let's go ahead and say, all right, we know we have 10 moles of KCl3 if we would stop at this point. But now, what I want to do is find grams of KCl3.
Oh, boy.
Now this step you've done already. You've probably done this step, I imagine, over 50 times at some point in this class. Because all it is a mole, 2 grams problem. So then what value goes down here?
That'd be the moles. So 10 moles.
Okay, we're not going to put the 10 moles down there. All we're going to do is put moles of KClO3 there, and then what goes up here? Grams of KClO3. So there's a tendency to write 2 in this spot, and you don't want to write any of these numbers other than 1. You want to write your mole ratios just in one location in your setup. You don't want to put 2 down here, because what we're doing here is we're relating not within the chemical equation or the chemical reaction. We're relating moles of KClO3 to how many grams it would be. So we would look up potassium, we'd look up 1 chlorine, and we'd look up 3 oxygens, and we'd find their weight. Okay? So potassium is 39.1 plus 1 chlorine, 35.45, plus 3 oxygens, which would be 48. And our answer up here would be 122.55 grams. Everybody understands how I got that, right? And everybody understands that that's the weight of 1 mole of, or molar mass of KClO3. So we go one more step, and we can find grams. So it would be 10 times 122.55, which our answer would be 1,200. And I probably want to stick with significant digits. We probably want to get back into doing that. So 15, it'd be just be 1,200 would be my answer. If I wanted grams. Okay? So what I'm going to do is we're going to look at one problem in the book. I'm going to have you do the first 2 steps to see if you can set it up. Based upon what I have up here, I'll leave this up here. Turn to page 308, number 1.
308.
Yep, 308, number 1. They give you the balanced equation. They're asking you to solve for how many grams of
Mercury.
magnesium oxides produced. So here's your equation. Mg plus O2 gives you MgO. And it's balanced for you. So again, top of page 308, number 1. And it says you have 2 moles of magnesium reacting. And it wants to know how many grams of MgO is produced. So 2 moles of magnesium is your starting point. And then what you need to do is end up with grams of MgO. I'm going to tell you the molar mass of MgO is equal to 40.3 grams. Okay? So that's the molar mass. So we know it's 2 steps to get there. Let's see if you can get there. So the first step, mole-to-mole ratio within the balanced
I
equation.
don't get that 40, whatever.
This is the weight you need in which to find the grams at the end. Okay? So Lindsay, up here,
That's so nice.
we had to have the grams at the end. So that's what you need that for. So I figured out for you, you don't have to. Usually you're going to have to do that.
So
You will have to do that yourself.
you already balanced for us too.
Yeah, it's balanced in the book. It's balanced in the book. All right, so down here has to be 2.
Yep.
And then we're relating it to 2 MgO. Any questions? So it'd be the same. It's kind of a silly question in a way because you go, okay, I got 2. I'm going to end up with 2. But to set it up, you can see how moles of magnesium cancel out. And now if we stop, we'd get moles of magnesium, and then it would just be 2. The next step, though, down here, again, there's a tendency to write 2 again. And you only do it one time when you do the mole ratio. So down here you put 1 mole of magnesium, and up above you put grams to that 1 mole, which is the molar mass. So basically it's 2 times 40, which would be 80.6. And that would be your answer. Okay? So the problems I want you to do associated with these 2 examples would be page 890. It's on the board. In your book, it would be problems 166, 167, and 170. Okay? And that's what you need to do. Show your work.
Do I have to make up anything?
No, you don't have to make up anything.